Now, I have 1 hour, and in this 1 hour, I want you to remind the graphical solution. I know last year, we really spent enough time on graphical solution, yeah? So I'll just remind you what it was, and then make some definitions at the very end so that you guys are ready for the simplex algorithm that we will start next week, okay? So, graphical solution of two variable LP problems. Again, I'll be too quick because I have covered this last year in 102. Suppose this is our problem. This is the famous problem that we keep solving, right? This is, well, we convert it to the general form, of course, maximize Cx subject to Ax less than or equal to Bx non-negative, and my Cx, A and B is like given in there, right? Okay, if you were to graph the problem that's given to us, this is the feasible region. Remember, we were writing each constraint, and then we were shading the part where the constraint is allowing to us. So this was named as the feasible region. The feasible region has points, and then this was our objective contours. We were defining them as isoprofit or isocost line, depending on our objective function. If it was a cost, we were saying it as isocost line. If it was a maximization problem, we were naming them as isoprofit lines. And we move in the improving direction as far as we can go until we leave the region, yeah? And C, the objective function coefficients were actually giving us our improving direction, right? So we move in the direction of C as far as we can go until we leave the region. For a maximization problem, the C itself gives us the improving direction. For minimization problem, we don't want to make C as large as possible, but we make it as small as possible. So we go in the minus C direction, all right? So C was our improving direction in the maximization case, and minus C is our improving direction in the minimization case. All right, so in order to get an optimum solution, we push our isoprofit or isocost lines in the improving directions as far as we can until we leave the region. That's what we'll be doing in here. We improve our objective until we cannot any further. Once we stop, if we go any further, we are out of the region. We won't be able to find any more feasible points that satisfies all my constraints, so that it was named as our optimum solution, right? I was also very picky in the names. So your optimum solution is the x vector. So the point 4/3 and 14/3 is the optimal solution. And the value, which is 46/3, is the optimum objective function value, right? Solution is the decisions that I'm trying to find out, right? So my point, the vector, is my solution, and my value is once you plug that solution in the objective function, whatever you get, okay? Is it too quick, or are you following? We're already done this, so I'm pretty much running, I know, but I have to finish everything in like 45 minutes. Okay? Do you remember? All right. Okay, so we first, example 1A was when we find this thing as the optimum solution, right? Now, I'm converting example 1B. So first of all, will the feasible region change? Is the feasible region changing or not? I can't hear you. No, thank you very much. It's the same feasible region, we're just changing the objective function. It's still a max, so we're gonna write another isoprofit line and move along that line. So we have already answered this, Improving direction is this different. It's again C, but our C is x1 minus 2x2. So our C is 1 and minus 2, so we move in this direction. So in the next slide, which point will be the optimum solution? Can't hear? 6, 0, thank you very much. So when I go along that direction, I leave my region at point 6, 0, which is the optimum solution with respect to this objective function. Another one, minus x1 plus 2x2. It's again in the same feasible region. Where do I leave the region? Oh, first of all, okay, let's play with it. With this objective function, can I have 5, 1 as the optimum solution? Where is 5, 1? Here. Can it be optimal? No. I go along, and I leave the region at 0, 4. Apparently, with this C, 0, 4 is the optimum solution, right? Now, yes, well, I changed the C again, minus x1 minus x2. In the same region, minus x1 minus x2. Optimum solution is 0, 0. Okay, we already had discussed this. There was this TV ad thingy, right? Remember, there was a radio ad and TV ad, and there were certain, I wanted to minimize the total cost, and I want to reach as far as possible. This is the formulation. Now you can easily formulate it. It's dead easy now after all that post offices and everything, but that was a challenge for you guys when you were in first year. Anyway, now we formulated it. We want to find the best solution. Here is the region, all right? And here's my C, but it's a mean cost, so I go in the minus C direction, and minus C direction leaves the region at point 7, 2, right? We changed the objective a little bit. Now we have, our objective function is 4x1 plus 14x2. So how were we naming this situation? What's happening now? What was it called? Yes? We have infinite number of optimum solution. What was this case? Is it unbounded? No. Unbounded means there is no optimum solution. There's always a better one. Here there is optimum solution. The value is 56. Every optimum solution gives you the same objective function value. What was this case called? Alternative optimum solutions. Thank you. Yes. Everybody's given the same optimum solution. How do we represent alternative? This slide is new. You didn't have this last year. Now, in order to, then that means there are infinitely many optimum solutions, which gives me the same optimal value, 56. Now, how do I represent that solution? I know there are two corner points, point 7, 2 and 14, 0. The line segment joining those 2 points are actually my optimum solution, right? And this is how you write that line segment. This is actually the convex combination of the 2 endpoints. So for any value of lambda, lambda being 1 gives you the first point. Lambda being 0 gives you the second point. Lambda being 0.5 gives you a midpoint. Right? By changing your lambda, you can find another solution with the same objective function value. Yeah? Clear? Change it again. I deleted one of the constraints. And here's the C. Now, what is happening here? This is unbounded. Because the definition of the optimum solution is it's the last point in the feasible region. Well, there is no last point. I keep going on, and there's always a yellow point following me, yeah? I cannot leave the region. Remember my true-false questions from last year? So how about we answer that right now? If I have a bounded region, Can I have an unbounded optimum solution? True or false? For a bounded region, can you give me an objective function value so that my problem becomes unbounded? Can you? No. In a bounded region, as I say, if the region is bounded, I'm going to leave the region at one point, right? So you cannot find an unbounded objective function value, unbounded solution with a bounded region. The reverse is not true though. All right, let's go on. So this is unbounded LPs. For maximization problem, I can increase my objective function as much as I can, and I never leave the region, all right? So it goes up to infinity. For a minimization, this time, in the my minus C is my improving direction, and minus C points out to infinity. It usually goes to minus infinity. How about this? What is the last case? Remember, every LP falls into one of the four categories. One, tell me. I'll show you. One, this. What was this case called? What is the situation? What did we find in here? This is not alternative. Look, it says optimum solution. Our value is 11.72. Look at the lines, red dotted lines. They're not parallel to any constraints. I'm leaving the region at 0.72 only. What was this case called? Unique optimum solution. Thank you very much. We have four cases. One, unique optimal, this one. Or, let's see, that one over there, right? Unique, only 1 point. What is the second case? This one. How did we name this? Alternative optimum solution. So I might be unique optimal, alternative optimum solution. Then we have this case. What was this? All right, then. What do you think this case is? Infeasible. If you try to find the region that all those constraints overlap, there is no such region. All right? You cannot come up with a feasible region. In this case, that's our last case that can happen, which is infeasibility. Yes? So here is our fancy slide saying every LP falls into one of the four cases. Unique, alternative optimum, unbounded, infeasible. Now, if the problem is unbounded, that means there is no optimum solution. All right? I don't care if it goes to plus infinity. Does it have an optimum solution? No. By definition, no. I cannot declare any point as the optimum point because there's another one better than that. There's always a better one, right? So in the unbounded case, we can never have an optimum solution. Then we played with many things last year. I guess I will have time for those discussions. But in order to have unique, alternative, or unbounded, the very first thing that you should have is feasibility. Very good. So you first check if you have a feasible region or not. If not, you can't say anything. The problem is infeasible, all right? If it's infeasible, no way for unboundedness, alternatives, no way. Nothing can happen. It's infeasible. Deal. Okay, deal with it. Done. All right, if it is feasible, then I can be talking about unique, alternative, unboundedness, all right? Keep that in mind. So how do we do this? What was the trick? We graph it. We first see if the feasible region exists or not, step one. Then we draw our isoprofit or isocost lines, depending on our objective, or we find our C, improving direction, all right? And then we move in our improving direction as much as we can until we leave the region, all right? Was this too quick? Half an hour? No, 20 minutes. I guess we're done with graphical solution, no? Clear? Questions? I have enough time to answer a couple of questions. Yeah, you're too shy because it was last year's topic. Okay, you just want to go home and go over them, right? Okay, how about, so did we notice anything about the optimum solutions? Let me bring you one of those feasible regions. Yeah. So what do you think about the optimum solution, the expected? Yes? They're on the boundaries and for especially corners, corner points, extreme points. Now last year we just named it like that. I don't know if today, me or next week, we will this time teach you. Oh, here it is. Now, I told you we will get a way to mathematically represent those points, all right? Okay, when you see it, okay, it's the corner there, but how would you represent it? Is by using convexity. Now, first I'll define a convex set, and for that I need a definition of a convex combination. So a convex combination of 2 points is actually the line joining them, yeah? That's what we did in the alternative solution. So you are given an x and a y. The convex combination of these 2 points is, for any lambda, you just draw the line in between, lambda x plus 1 minus lambda y, for every lambda, including the endpoints, okay? So lambda being equal to 0 gives you point y, and lambda being 1 gives you point x for this example, okay? Now, this is a definition of convex combination. This whole thing all right. Yeah, may I check? Thank you. This is a definition of convex combination. Now, the definition of a convex set is what's written underneath that. A set is called convex if you pick 2 points and you look at the convex combination for all lambda. If every point in their convex combination function is also in this set, we name that set as the convex set. Got it? So a set becomes convex if you pick 2 points, draw the line. If all points on the line is in this set, we define that set as the convex set. Okay? Let's see. The first rectangle there, is it convex? Is it? For any 2 points you pick, draw the line, always in between. Second one, the triangle opening up. Is it convex? Yes. Circle? Yes. The one here, my thinking is not working, so this one. Is it convex? You pick 2 points, are you always in the set? Try to be out, you cannot. How about the one next to that? It's not, because if you pick the 2 endpoints towards the ends of these, you're not in the set anymore, right? The 1, 2, 3, 4, 5, 6, and 7, are they convex? No, because if you draw the lines, they're not always in the set. Now, this is a very nice proof. I suggest you all try it. So that's a feasible set of an LP, yeah? X in Rn, AX less than or equal to BX non-negative. This is how we generalize our mathematical models in linear programming, right? I don't care about the objective function. This is the feasible region, right? So AX less than or equal to BX greater or equal to 0. I'm claiming that it's a convex set. Now try it on your own. Prove that the feasible set of an LP is convex. Okay? So how would you do that? You're going to pick 2 points. Then you're going to take the convex combination, and you're going to show that the convex combination is still in this set, which means still less than or equal to B and non-negative. If they satisfy those conditions, they will be in my set. Yeah? Got it? Yes? A is my matrix. All right, let's go all the way back. How do I do that? Here's my A and B. Yeah, here's my A and B. A is called the coefficient matrix. B is called the right-hand side vector. C is called the objective function vector, right? They all have in their own domains. C is 1n, B is m1, A is mn. Okay? Now, where did I stop? I was claiming that the feasible region, oh, here we are. Feasible set of NLP is convex. Now you're supposed to prove that is true. Okay, try it. Okay, another definition then. In order to represent the corner point, I need another convexity definition, which is strict convex combination. Now, it's very similar to the convex combination, you just don't include the endpoints. So lambda is between 0, 1, 0 and 1, not included. Okay? Then the combination vector is called the strict convex combination. Okay? Because for every lambda, you get a new vector, yeah? But this time, I don't want the original vector zeros and ones with the zeros and ones. I only want the middles. Then it's called strict convex combination. Okay? Then my extreme points. Well, a point in a convex set is an extreme point if it cannot be written as a strict convex combination of other 2 points. So if you don't let 0 and 1 to be included in your convexity definition, then you can't be able to write your corner points. That brings us to the definition of the corner points or extreme points with using mathematics, right? If you cannot write that point as a strict convex combination of other 2 points, that means that guy is a corner point. It requires lambda being 0 or 1 to be represented. Because in a convex set, you can represent any point by a convex combination of other 2 points. That was the definition of the convex set. Everybody is in the set. So you pick a point, you pick 2 different points, write the convex combination, that's what your point is. And normally what we do is any point in a convex set can be represented by the convex combination of the corner points. Just pick 2 corner points, anybody in between can be written by them. Yeah? But a point then is a corner point if you cannot write it as a strict convex combination of 2 other points. Because for corner points, you need lambda being equal to 0 or 1. This brings us to our fundamental theorem of linear programming. Okay? This is really crucial. We utilize this theorem a lot in proving other theorems. We're not going to prove this in this course, but it really is crucial. It's the fundamental theorem. Yeah? Let's read it. If the feasible set is not empty, then there is an extreme point. And B, if the problem has an optimum solution, then there is an extreme point which is optimal. Now let's read it again. Fundamental theorem, part 1 says, if there is a feasible set, then there is an extreme point which is feasible. Fine. Part B says, if the problem has an optimum solution, then there is an extreme point which is optimal. All right? Be careful, these are not if and only if type statements. Both are if then type statements. All right? So part B says, okay, you solve it, you get an optimum solution. You get an optimum solution, when do we have the optimum? Either in the unique case or in the alternative optimum case. Unbounded, I don't have an optimum solution. Infeasible, I don't have a region anyway, right? So when I have an optimum solution, it's either unique or alternative solutions. Now, fundamental theorem part B says, if you have an optimum solution, then there is a corner point which is optimal. Well, if it's unique, that's how we find it anyway. That was the corner point. In the alternative optimum solution, remember we had 2 corner points, not even 1. Yeah? So there exists a corner point which is optimum. Got it? And part A says, part 1 says, if the feasible region is not empty, if it is defined, there's at least 1 corner point in it. That's what it says. All right? Now, this fundamental theorem of LP actually will be utilized in developing a general algorithm that we can use in Rn. So in R2, yes, we find graphical solution, we find the optimum solution. Real life is never having 2 variables, right? How are we going to do that? Well, the idea is the same. Apparently, there is a region, and I'm trying to leave the region in my improving direction. So the graphical solution method gives you the idea. Now, how am I going to do that? So I got the point that the optimum solution is one of those corner points. So what if I just look at them? What if I just find the corner points only? Check the corner points only. That's what we're going to do. The fundamental theorem says in part 2, you know what? If there is an optimum solution, there is one which is a corner point anyway. So yeah, I'm safe. And also if the feasible region is not empty, if I'm not infeasible, then there will be corner points in it. That's fundamental theorem part 1. So by utilizing this theorem, we could actually convert our knowledge that we gained through graphical solution to general N. What are we going to do? We're going to look to those corner points. So we were going to devise an algorithm that will check extreme points only, because it's enough, right? So instead of infinitely many points within the region, I'll only check the corner points. Got it? Now these remarks remind me the exam questions we had last year, right? There exists an objective function such that every corner point is the unique optimum solution, right? I was giving you a region and I was asking, give me an objective function so that this problem becomes unbounded, this problem becomes infeasible, blah, blah. If I give you a region, would you be able to give me an objective function so that this problem becomes infeasible? I can't hear you. No. If I give you a region, you cannot give me an objective function that makes this guy infeasible. Being feasible or not has nothing to do with the objective function. All right. Then, all right, I give you a region. The region has corner points. And I'm asking you, find me an objective function so that point A is the unique optimal solution. What was the trick that you guys are using? You were trying to come up with an objective function so that your improving direction leaves the region at the corner point that I specified, right? And for every corner point, you can come up with such an objective function, which is actually what you were doing is you're trying to exit the region from the cone of exit. That's how we call it, how we name it, right? This is the thing in red lines, all right? For the point X to be optimal, you have to leave the region from the cone of exit of X, okay? So your C, if your C is in between those red lines, then your point X is your unique optimum solution. Right? Clear? We have already discussed the second one. The first one we did, okay, for every corner point, you can devise an objective function in which you're actually defining it with the cone of exit of that point, okay? And the second remark says, in order to have the LP unbounded, the feasible region must be unbounded. That's what we just discussed. If the region is bounded, you cannot find an objective function so that your objective is improving all the time. Because your region is bounded, you're leaving the region. So, first of all, the necessary condition to have an unbounded solution is to have an unbounded region. Okay, I have the unbounded region. Now, is all my optimum, for all C, my problem is unbounded. Is this true or false? I gave you an unbounded region, and I'm saying you fit over this region, for every objective function, your problem will be unbounded. True or false? False. Why? We just had it somewhere there. You may find, yeah, like this. Unbounded region, but I'm getting an optimum solution, right? So it doesn't have to be true. The reverse is not necessarily true, was the statement. Oh, it's here actually. So this whole thing, so for maximizing C equals 1 and 3, x1 plus 3x2, the problem is unbounded. If you want to minimize it, the problem has a unique optimum solution. If your C is minimizing 1, 0, so if you're minimizing x1, you have alternative optimum solutions. Right? Question. That was a too quick hour, I know, but because it's just reminding you the things that we have spent like 2 weeks last year, I don't need to spend another time on it. Any questions? Okay. See you in the practice sessions tomorrow, then, because we have practice sessions this week.